You know, what's the threat space? What are the surfaces on which systems can be weak and how they can be exploited? So remember that, you know, an IoT, if this is an IoT device, it can be attacked at the chip level. Somebody just noted that all the chips produced by Intel in the last, you know, in the last few years are subject to a major security flaw, and manufacturers these days are figuring out whether or not they can solve it in an efficient way. Yeah? So your chip could have a flaw, or perhaps there is no flaw in your chip, but on your board, if I got access to the board, I could send signals on certain buses and extract information out of memories and compromise it. Conversely, you know, it could be that at the whole product level, I have some interfaces by which I can just interact with the product and ask it questions by which it leaks information. Just like that video camera where I gave username and password and got all the information. And some of these attacks are happening on the local network, like the Wi-Fi or the Bluetooth network where these devices are, but a lot of them can actually happen over the internet. So people are now building, just like Google is an engine for searching interesting content on the web, people are building deep search engines which will reveal many types of IoT devices, all the protocols they're using, all the ports they're using. And so you can have a global way of figuring out a large number of devices which are vulnerable. Okay? And now you can do remote attacks over the internet through that surface. Now there are very different ways in which you can think about how to put security into these systems. So I've listed some of them. One of them is that each device should be able to at least tell you who it is. It should account for itself. It should tell you whether it's up or down or what is its health. So at least for each device, there is a basis for saying, how many devices do I have? Are these devices stolen? This is a big problem for industrial IoT. Yeah? I deploy 5,000 sensors, but how many of them are there today? And by the way, could it be that somebody has put in a new sensor which I can't account for? That's an equal risk. It's not just the sensor slips away, but a fake sensor is put there. So can I account for these? The second model is recoverable. Yeah? That instead of having to go to a device to touch it, to swap out the board or to change its software program physically, can I conveniently update that device just like your phones are updated? So your phones are updated in the field, right? So all IoT devices must allow for some mechanism by which they can be programmed remotely, but also in a secure way from their enterprise controller. And of course, to whatever extent possible, you should have the notion of trust through some form of authentication. And again, authentication is a subject that you may or may not have been exposed to, but certainly you're users of authentication. Every time you log into your Facebook account, you're being authenticated, right? But is it possible that the authenticator is itself compromised? What happens if the enterprise controller who is checking about the user of this IoT device is itself compromised? So this is increasingly starting to happen. So how many of you are familiar with a prompt that shows up on your phone which says, do you trust this certificate? Yeah. Do you see that happening from time to time? Yeah. I moved to Sahyadri, and Sahyadri is offering me some certificates which are saying, this network is a Sahyadri network, and this is the key associated with it. Yeah. And I hit, yes, I trust Sahyadri. But why did I hit it? Did I actually know that that certificate was true? Yeah. A lot of our reactions are psychological. I have been invited by Sahyadri. I therefore trust Sahyadri. And something is saying, this is a Sahyadri certificate. But it could be you who sent me that certificate saying this is a Sahyadri certificate. Right? So it is increasingly turning out that the backbone of authentication for the internet was the public certificate system. And that backbone is no longer very trustable. Some certificate authorities have been compromised, and some very large agencies like, departments of defense in major countries have had their authentication systems compromised. So that assumption has to be changed, and that's causing all the excitement in what is called the blockchain right now. So many of you may have heard about, how many of you have heard about cryptocurrencies? Yeah. So long ago there was eCash, now we are using things like Bitcoin. And the idea in all of these currencies is that we never trust one agency. In order to be robust, what you say is, I'm not going to be dependent upon something like a government, that all of us conceptually can be part of the government. I'm a government, you're a government, you're a government, and we will all replicate all the transactions happening on the Bitcoin. And the underlying computer science primitive for doing that is called the blockchain. A blockchain is simply a chain of all the transactions, and there is a way of checking the integrity of this chain. And now, if we can use blockchain as a basis for authentication, we can have a distributed, non-centralized government-based way of protecting the authentication of our IoT systems. So there's a lot of interest in that concept. So there are different models where you engineer security at design time. So you just combine your solution and integrate security into it, or you change the security at runtime. Some solutions can work even if you don't know how the application works. Other solutions depend upon a detailed knowledge of what the structure of the application is, so they are white box approaches. And here are some of the ways in which you can create exploits. So the first, this one is worth keeping in mind. We all use things like keys. And the use of keys, that science is called cryptography. Cryptography is hard to implement because there are many ways in which programs which work correctly under the normal conditions can be put into abnormal conditions. Because I didn't anticipate that this program could be given this kind of input, or inputs in this sequence. Because it's hard to program in that way, many implementations of cryptography are actually insecure. So the advice for you is, as you are going through your curriculum, understanding how to use crypto, you should be tempted not to write your own implementations, but to assemble implementations from existing libraries whose components are secure, or to use existing implementations. And if you become even more advanced, then you can become a developer of these libraries, where you know the right engineering practices for programming secure primitives. So this is one of these areas where every year some new cryptography shows up, and then I ask, should I use this lightweight cryptography? And the answer is, you can use lightweight cryptography only after it is trusted by the whole community, and it has very good implementation. Okay? Otherwise, it becomes insecure. So there are problems in software, problems in configuration. Most of the problems are because these devices are just lying out there. I mean, maybe your access points are hard to see, but sometimes, at night, maybe you can go to your access point and attach a USB device to it, right? And that can monitor things which are happening on the access. Jonathan, how am I doing on time? I have 5 minutes. Okay. So this slide makes the point that the technologies for IoT are divided between device technologies and technologies in the core network. Okay? And interestingly enough, most of cybersecurity is happening inside the core network. Okay? Very little cybersecurity is actually happening inside the device network. Okay? And that's where there's room for innovation. There's a lot of opportunity here which you folks can work on. And we need to balance both of these, because ultimately we need to make the device better, But when the device is compromised, this one has to do a good job of learning how to deal with it. Now, when you work on the device, there is a choice between using rich software frameworks or using interesting hardware frameworks. So there are small modules called trusted platform modules, which exist in every laptop. And they become the actual basis for building the security step by step in your laptop. And we are learning how to make these TPMs fit into the many processors which exist on the IoT device. But the alternative is to say, every year you're putting more and more transistors on these IoT devices, so you can run more and more software. And if you have all this software framework for security, should you use that? So the answer is, it depends upon which IoT device you're using. If you're using a smartphone, the trend is that security software is dominating. But if you're using Arduinos and modes, then the hardware security is dominating. Okay. 2 or 3 very quick notes about how you realize these concepts. So the first concept is, as I told you, these new systems on chips have got FPGAs in it. And those FPGAs have got some secure primitives inside them for symmetric or asymmetric crypto, etc. Now, what you need to do is to program inside the FPGA a small bootloader which can reload the entire configuration of this device. And there is some small checking mechanism which keeps telling it that the operating system is behaving correctly. So you need some very small checkers which should be very hard to reach inside the hardware. So not only should the FPGA SoC have very secure interfaces, but there shouldn't be programmatic ways in which you can reach those registers and change these detector configurations. But then your operating system has to support the secure primitives that you need, like the secure boot, the secure contact with the enterprise, and how you recover individual apps. All this should be at a very low level in the operating system. So there is a lot of work going on in rewriting the operating systems to make them secure in this way. And of course, on top of that operating system, you can have apps which are inside virtual machines. And because there is a sandbox here, ideally they should not compromise this trusted base. So what we are saying is that this is essentially a hardware-supported implementation of security, and whatever you need in software is at the lowest level of the software stack. So let me tell this story just to make the point that after you have built a secure operating system, you still need to think about the protocol with which you interact with the enterprise to protect yourself. So the story goes like this. You know, at Ohio State, I teach a class like this, where I go into a room and I log into a computer with my username and password. Yeah? So this student puts in a USB key inside that computer and he logs my username and password. So he has compromised my account. Okay? Now this student has also compromised the account of a colleague of mine. Yeah? His name is Wayne. Now the university tells me and Wayne that we cannot disclose the name of the student until the entire case has been analyzed for protecting the privacy of the student. But Wayne and I want to know, is it the same student who has compromised me that has compromised you? So this is an example of a cryptographic protocol. I am going to talk to you and prove to you that I know who has compromised me. Yeah? And you will prove to me that you know who has compromised you, and the protocol will tell us whether both of us have been compromised by the same person. Now, the interesting thing about this protocol is, if you have not been compromised, you will never learn that I have been compromised. Right? And if I have not been compromised, then you will not leak that you have compromised me. Yeah? So in that sense, both of us are protected. So we can do cryptography in a way in which I have a key, you have my key. I can prove to you that we have the same key, but I will never reveal anything about my key or even that I have a key unless you have a key. Yes? This is the nature of cryptography. It's these very interesting puzzles that you're solving. But if you can solve this problem, then you can essentially use the same key infinitely. You will never have to change the key. And this is a good idea because part of our problem in security is that keys, every time I use them, they become weak. If I show you how this key is used to encrypt this data, and this data, and this data, by the time I have shown you many, many data encryptions, you can guess what my key is. But if I solve this problem, I am not leaking that I have this key, and you discover I have this key only if you have the same key. Yeah? So we need a new class of cryptographic protocols. So as you folks start studying security, you can start inventing ways in which we can make crypto maintenance overhead much lower. So Janardhan, this is the problem you were asking about. How can we reduce the maintenance cost for security? Okay, so in the last couple of minutes, I wanted to make the point that the expenditures in cybersecurity are growing quite phenomenally. At the same time, the cost of cybercrime is growing at a whole other level. So as you can see, it's several trillions of dollars which cybercrime is dealing with today. So initially I showed you all the gory examples, but I also want to tell you this affects national productivity. Yeah? And the IoT market in particular is extremely weak in this space. So you will see a lot of growth in the cybersecurity area. And as I said, network security is much better handled than device security, but network security is using artificial intelligence now. So remember I said that virus checkers no longer work? So now we do behavioral checks. We are studying all the behaviors that these networks are doing normally, and then we are learning models of what looks like a deviation from the normal model. So we are using deep learning networks as a basis for saying this IoT control system seems to be under some kind of a usage which I have not seen before. Therefore, let's go investigate. A lot of new options are showing up in devices. And in particular, even the small motes that I was talking about, we are able to program very interesting trusted execution environments on them. So many folks are coming into this space, and I'm hoping more and more Indian companies will join here. Because if you wanted to make in India, as Serge said, you've got to discover in India and invent in India, but please also learn how to protect in India. Yeah? Because it's a competition. And other nations benefit if they can compromise your technology. Meanwhile, lots of new opportunities showing up because you have new types of hardware, new types of crypto, the ability to compute near the edge, and all this new meshes, right, which can let you do much more computation close to the device. So let me summarize with this. This is a wave, right? We started off with Bell's law, and we said there is a new generation of computing. It is the IoT generation of computing. And so it's going to be exciting. That said, this wave is putting us in a connected and interdependent world where these attacks are touching us. Right? And so you really have to learn to deal with the technical aspects, but also, hopefully, the policy, governmental, legal, and economic incentives are also dealt with. So expect a bumpy ride, but you can help. That's my main message. Get involved in being part of the solution before it's too late. Okay, so with that, let me thank you for your attention.